Hello, I am Gigio and welcome to the video. So I was the leader for this week's experiment, which is experiment 5, bending moment. This experiment had an objective to understand and measure the action of moment of resistance in a beam, which is bending moment. To summarize today's report, different loads were applied to a beam at a certain location by a load hanger. Then the spring balance is adjusted until the meter is balanced and the reading is of spring balance is recorded, and calculations were made throughout our process, and we managed to find our results and discussions as well. Now we move on to the theory of the experiment today. Bending moment is the product of force applied on a beam with the distance between the point of application of force and fixed end of the beam. When an external load or the structural load applied in the beam is large enough to displace the beam from its present place, then the deflection of beam from its present axis causes a bending moment on the beam. When a beam is loaded by forces and couples, internal stress and strains are created. So let us take a look at these figures labeled figure A, B, and C. So consider this cantilever beam is cut through by a vertical force P, which is figure A. So now imagine that beam is cut through at the cross section S as in figure B. So Qx, which is the shear force and the bending moment, are assumed to be positive in the directions as shown in B and C respectively. The positive direction is vice versa if the right hand part of the beam is considered. So for the vertical equilibrium at part A, there must be a shear force acting on it as shown in figure B. So n is equal to negative Ra. For the vertical equilibrium of part B, the shear force evidently acts as shown and has the value of P minus Rb. So the formula for the equilibrium in parts A and B are shown on the screen as well. So that is all from me. I will pass to the next presenter. Thank you and Merry Christmas.
Good day everyone, I'm Keshvini and I will be explaining about the methodology of experiment 5 bending moment. First, the apparatus used consists of the experimental beam followed by the loads of 10 Newton and 20 Newton followed by the load hangers P1, P2 and P3. For the next part, I will explain the experimental procedure of this experiment. The beam was divided into two parts, smaller part A, larger part B, and was connected by a joint, thus forming a frictionless hinge. A moment of resistance about the hinge was provided by an underslung spring balance, which acted at a lever arm of 150 mm. There were three load hangers placed on the beam to induce load onto the beam and two bearing on stands to support the beam. Spring balance was done each time after the load was altered and the reading of the spring balance was recorded after that. The measured bending moment in Newton millimeter was 150 times the change in the spring balance reading. So the procedure goes like this for part 1. The beam was set up so that the bearing pin in part B was 300 mm from the left hand support and 600 mm to the right hand support. One load hanger was placed on the middle of the smaller part A of the beam and one of the larger part B, and the third one at the joint just over the bearing pin. The two parts of the beam was aligned using the adjustment on the spring balance and the initial reading was recorded using table 1. The 10 Newton weight was hung on part B. The beam was realigned and the new reading on the spring balance was recorded using table 1. The difference between the two readings was the effect of applying the 10 Newton weight on the beam. The distance was recorded using table 1 from this weight to the right hand support. The procedure was repeated by using the hanger over the bearing pin and then the hanger on part A. Finally, the whole procedure was repeated by using a 20 Newton load. Consequently, for the part 2, the three load hangers were placed as desired. The beam was aligned and the initial reading of the spring balance was recorded using table 2. The weights were put on all the three hangers and the beam was realigned and the new spring balance reading was recorded using table 2. The experiment in part 2 was repeated with different positions and loadings. The new spring balance reading was recorded using table 3. That is all for the methodology part. So I'll pass the experiment presentation to the next person. Thank you.
So I will proceed with the calculation part. So this is basically the overview of the Excel calculations. So for part 1, when P1 equal to 10 Newton, the summation of Fy equal to 0, we obtain Ra plus Rb equal to P1. So summation of moment at point B equal to 0, we obtain Ra times by 900 minus P1 times 800 equal to 0. Then we calculate, we obtain 8.89 Newton for the value of Ra. So and then we do the summation of moment again at point C. We obtain 8.89 times by 300 minus 10 times by 200. We obtain 667 Newton millimeter, which is the theoretical value. For the experimental value, we just multiply 4 by 150, we obtain 600 Newton millimeter. So the calculation was repeated using the same technique to obtain for the value of P2 equal to 20 Newton. So for part 2, the calculation is quite same. So for example, when P2 is equal to 5 Newton, we do the summations of Fy equal to 0, we obtain Ra plus Rb equal to P2, and then clockwise summation of moment at point B equal to 0, we obtain Ra times by 900, which is the distance, minus P2 times 600 equal to 0, we obtain Ra equal to 3.33 Newton. So this value then used in the summations of moment at point C times by 300, we obtain the theoretical value for which is 1000 Newton millimeter. And then for the experimental value, we just multiply 7, which is the net force, to the distance 150 millimeter, then we obtain 1050 Newton millimeter. So for the last part, let's say we have P1 equal to 5 Newton and P3 equal to 12 Newton. So we do the same summation Fy equal to 0. We obtain Ra plus Rb equal to P1 plus P3. So summation of moment at point B, where clockwise is positive equal to 0. We obtain Rb times the 900, which is the distance, minus P1 times 100 minus P3 times 500 equal to 0. Then we obtain Rb is equal to 7.22 Newton. So to calculate the value of Ra, we just minus the total value of P1 plus P3 minus the value of Rb, we obtain the value of 9.78 Newton for Ra. So the summation of moment at point C, we obtain 9.78 times 300 minus 5 times 200. The theoretical value is 1934 Newton millimeter. And then for the experimental bending moment, we just multiply the net force to the distance, then we obtain 1500 Newton millimeter.
Hello, I am Jasmine and I am going to talk about the discussion in this experiment. So the first question asks, when the load when the load was double in part 1 of the experiment, did the bending moment double? And we are to explain our answer. So firstly, the bending moment indeed doubled, because when the load increased, the bending moment also increased. So for example, when the P1 is equals to 10 Newton, the experimental value of the bending moment is 600, while the theoretical value is 666.67. And when P2 is equals to 20 Newton, the experimental value of the bending moment is 1200 Newton, which is the double of the 600 Newton from when P1 is equals to 10 Newton. And the theoretical value obtained in P2 is 1333.33 Newton, which is also the value of 666.67 when it's doubled. In the part 2 of the discussion, we are to compare the average figure for each of the experiment by using the bending moments values obtained from the experimental and theoretical. So in this one, we chose to use percentage error instead of ratio. So the percentage error formula is theoretical value minus experimental value over theoretical value times 100. So in P1, when the loading is 10, the experimental value is 600 Newton meter square, and the theoretical value is 666.67 Newton meter square. And the percentage error calculated by using this equation between these two is 10%. And when loading in P1 is equals to 20 Newton, the experimental value obtained is 1200 Newton meter square, and the theoretical value is 1333.33 Newton meter square. And between these two values, the percentage error calculated is 10%. And then in P2, when the loading is 10%, 10 Newton, the experimental value is 1800. Theoretical value is 2000 Newton meter square, and the percentage error is 10%. When the loading is 20, experimental value is 3600 and the theoretical value is 4000. The percentage error calculated is also 10%. In P3, when loading is 10 Newton, the experimental value is 900, theoretical value is 1000, and the percentage error between these two is also 10%. And when the loading is 20 Newton, the experimental value is 1800, theoretical value is 2000, and the percentage error between these two is also 10%. So this is the percentage error for results in table 2. When the loading is P2 equals to P5, experimental value is 1050, theoretical value is 1000, and the percentage error is 5%. And the loading is P1 equals to P3 equals to 10, and also P2 equals to 5. The experimental value is 2700, theoretical value 2666.67, and the percentage error is 1.25%. In the percentage error for results in table 3, when P1 is equals to 5, P3 equals to 12, experimental value is equals to 1500, theoretical value is 1933, percentage error is 22.4. As for P1 equals to 5, P2 equals to 10, P3 equals to 2, the experimental value is 2400, theoretical value is 2600, and percentage error is 7.69%. So from this experiment, the average percentage error values for both 10 Newton and 20 Newton loads may happen due to some errors encountered during the conduction of this experiment. For the bending moments in part 1, the percentage error is quite small, as we can see just now. so it is proven true. The errors that may occur in this experiment are as shown. As for instrumental error, the scale of spring balance is not accurate enough to get exact value. As for random error, hanger may move around when beam is being adjusted throughout the experiment. So the precautions that we have to take care of is, firstly, use precise and fully functional spring balance. Secondly, make sure the position of hanger is accurate during any adjustment. And lastly, we are also to make sure the eye level is perpendicular to the scale of reading. So the conclusion of this whole experiment, based on the experiment results, when stress is doubled, the bending moment will double as well. Secondly, bending moments are acceptable based on the theory, since the percentage errors are within the value of 1.25% and to 50%, as we can see just now in discussion part. And thirdly, this difference between theoretical and experimental values are very small. Thus, we can deduct that the theory is verified even though there are little errors. So that's all from our group 2. Thank you.